Okay, okay, I'm standing in some odd time now between your lunch and the session. So I'll try to be fast. And I think some of you have already heard about Spotlight. So here the main aim is actually basically to kind of bring out the features which are specific to Spotlight and which can be useful and may have some learning from it, like as we went through. So anyway, so this is the cluster. Let's move ahead. So it's a team is actually the is behind the project, and some of the faces you can see, some of the people are here who are helping, and then the team members are all here. So it's a kind of effort putting by a big number of students, postdocs, and engineers from GMRT to get the thing happen. So again, on slide, a few seconds for GMRT, because this all things is based on GMRT. So GMRT, as we are hearing about DSA, Meerkat, is also one of the interferometer. Is operating frequency might be a little different from the other interferometer, running from 100 megahertz to 1500 megahertz. Baseline is 25 kilometers, which is important because that gives us the localization accuracy. And there are 30 antenna and 45 meter dishes. So like compared to other interferometer which you heard till morning, the GMRT dish is larger, which is giving us a large collecting area. Sensitivity is more, but it is actually giving us a less field of view. So GMRT is an excellent instrument. It become even more interesting when this upgrade of the bandwidth happened towards the like late 20 and like last few 4 or 5 years back. And then after that, it took some time to stabilize the system last few years. So now it is almost the time where actually you can expand GMRT for doing something interesting for the, which is called common source searches. Like as you heard from Kaustav in the morning, that Meerkat is going towards the mid-trap project, which is a common source searches. So like when you build something in interferometer, the problem with interferometer is very good, having a very good resolutions. It gives you localization, but the field of view is minimized. So because to improve the field of view, we actually try to make the system available 24/7, which make the thing commensal. So that is what the same thing Spotlight is trying to do with GMRT, even though GMRT has a very large collecting area, very good sensitivity, but it was lacking the commensal facility. So as you can see in this transient landscape, so it was the GMRT with the incoherent beam, which you also heard in the morning. So because you get a large field of view, but the disadvantage or the difficulty with dealing with incoherent beam is that it actually comes up with a lot of interferences. Because the way the sum happened is actually prone to have a lot of interferences, and also is sensitivity. So as you can see in this curve, which is very clear, like if you want, when you're pushing it down, you're improving in sensitivity because you have a Spotlight which is like coherent addition. And when you have a coherent addition, you will push in both sides, because now you have a much more interference-free baseline. So you can actually go to the smaller as well as higher time resolutions. Increased pulse width basically. So because your baseline is much more flatter. So that's the beauty of going from incoherent to coherent. So you gain in the sensitivity as well as you gain in the parameter space of the pulse width. So now, what about Spotlight? So I'll talk about the sources which Spotlight is. So you already heard about some of the things, but my point will be to kind of summarize and bring it out something which maybe we have missed last week while we were discussing. So Spotlight, if it is work in the full specification at which is kind of proposed to build, is 2000 beams on the sky in real time. And then we'll be kind of seeing 200 plus FRBs over next 3 years of operation, which is like right now funded, and which will come out to be like 1 or 2 FRBs per week. And we have a DM space, which is like a different DM space in the frequency space. As we understand, like as you go to higher and higher frequency, your transient buffer length reduces, and you can actually go against the dispersion and scattering. So that means you can increase your DM length. So you go higher DM and the higher frequency. But in the lower frequency side, which is go all the way up to 300 megahertz, you limited 2000 parsec per cubic centimeter. So this bar chart is actually based on the last 3 years of GMRT operation. So the way GMRT operated is kind of biannual observation. So in that, you actually, everybody propose, and then based on that, you see what fraction of GMRT time goes into various frequencies. So this is we call band 4, which is almost 50% of GMRT time get used in the band 4, because that is the most popular band in GMRT. And you spend maybe like 1/4 is actually in the band 3, and then like 10% of time in band 5, and rest is remaining in the, which goes to multi-frequency observations, as well as band 2, which you don't cover. So the spectrum which you cover is all the way from 300 to 1500, which is basically band 3, 4, and 5. And then as you can see, based on the percentage of time you spend on the sky for a particular band, you can come up with the FRB rate, which actually you can see in this rectangular box, which is 3 years of operations. So now, so it has various things as you just try to capture here. It can search for pulse width up to 10 seconds. It can search for long period transient, which you hear last few talks also. And so now, if you were to capture in one sentence, what is the kind of right now the status of the spotlight system? We have 160 beam system kind of operational from May 2025. So this operation in the sense like it see the first sky in May 2025, and then we are actually, as every system, when you go to the first time in the online mode, we have various things to sort out the system. So as we are deploying and are observing the simultaneously, so we actually last few months we are kind of sorting out various systems, but both the fund of kind of bug in the pipeline, kind of meeting the sensitivity limit which you have proposed to. So now the system has right now reached to a stabilized location where actually you're meeting the expected sensitivity, but we have limited number of beams. So I'll come to that. So now, when you actually try to run the simulation, try to understand what are the parameter probes parameter space you are probing, and basically, as I think you heard about last week also. So Spotlight is sitting in a space like where basically you see this picture we have seen from Kriti, how the FRB are kind of populating the GMZ plane. And you can see the almost 50% of the predicted population of Spotlight is going to fill up this part of the redshift. So which is actually where there are some voids. So and Midcut is pushing this towards the right. So it's kind of sitting in a nice space between the current population which we have seen and then the population which are coming out from the mid-trap project. So hopefully if this population comes out, it will be not too far, not too near that kind of population Spotlight able to probe. So a bit more on the pipeline. So as any kind of common source search pipeline, it has multiple components, and since GMRT is a kind of interferometer, it will have both imaging as well as the beam forming capacity, which are kind of captured here. So we'll have a beam forming capacity where you can actually do time domain search, and you create 3 different products. So you create a beam buffer, which is basically on which transient search happened. And I'll tell you how the beam is generated. It's not really the tidal beam which you see. It's a little different. It's formed from the visibility. So that gives us a real-time imaging capability. So you get a real-time imaging capability which is triggered by the detection on the beam. And then once the detection happens, you have baseband buffer also. So we have 400 seconds of transient buffer. Either you talk about beam, visibility, or the baseband. In each of the cases, we have 400 seconds of transient buffer. That makes the memory requirement almost of 50 TB or something, which is a very high memory requirement because we go all the way up to 300 megahertz, which is actually much smaller, and then dispersion so is much larger at the low frequency. And this is 60 servers, and there are 800 GPUs, hundreds of them, and then we have a 2 petabyte storage, which is kind of split between the long time archive and short time archive. So the way we are operating right now, we have a rapid science which operate for a week time scale, and you have a data intensive science which operate on a 6 months time scale. And you have product like beam, when you actually get an ArcMinute or sub-ArcMinute localization directly from the beam data. And then followed by you have a real-time imaging, which push you to the arc-second localizations. And then you have a quasi-real-time pulsar search, which I'll come up later. And once all these 2 things are satisfied, then you get a baseband data dumped, and which will allow you to build up on the higher time resolution as well as polarization properties of the burst. So I'll talk about few slides which basically try to bring out that what are the maybe a little bit different we try to do, and which kind of show the power of interferometer. So one is that I think you have heard about this in the morning also from when Robert actually tried this thing. So this is actually it's called PC beam. It's a post correlation beam versus PA beam, which is a phase direct beam. And as you can see in dynamic spectrum and as well as in the bow tie array, the PC beam, post correlation beam, which is built from the visibilities. So we actually add the cross terms of the visibility to form these beams. Since we form the beams from the visibility, you can do that. And it's much cleaner, which will help us to basically detect as well as classify both things. And the same thing you can actually see in the folded profile plane. So it's the pulsar, which is folded profile. And you can see the PC beam, it looks like much flatter baselines, which is important for when you do search because it is much flatter baseline, as well as here also you can see baseline is much flatter, which will allow us to push the pulse width at which you can search for. And definitely to give you more sensitivity compared to the PA beam, which is a simultaneous data. In addition to that, you will also see when you see in the image plane, the beams look much cleaner in the PC compared to the PA because you have the incoherent sum, the self terms addition, which makes those side lobes and the little broader beams, which you get much more cleaner, which will also help us to kind of localize because you have a much more cleaner beam. So now how we do this thing. So you, as like you heard from Mekhla last week, that actually talks about various kind of tiling and various kind of modes. So we kind of operate in 3 different modes. So one mode is like we have a commensal mode where you don't have any idea where the sky is, like all the other surveys are doing similar thing. And then we have a mode where we are doing a targeted field of view. So we actually know what to observe for. And like this is a kind of open sky time. We have also given hundreds of open sky times, so 200 beams on that. And we have a tiny clusters mode, basically when you try to do a multiple sources or multiple field of view, but they are separated. So you can put a cluster of beams around that. And then last mode is kind of VO triggered event. So you actually, if you get a real-time VO triggered, you can form the beam. This is under construction, but something is going to happen. So then you have a tiling based on the real-time trigger. So these are the different modules support, but all the beams which will do will add up to maximum 2000. So you have to sacrifice the commensal beams if you enable all the other modes coexisting with that. So again, another new features or something we are trying to do in things is basically how to improve the sensitivity of GMRT, basically how to reach to the raw sensitivity of GMRT. That means how you can actually combine this antennas in the phased manner, because effectively you are phasing the antenna. And as you can see in this plot, this is a time and this is a sensitivity. So you can see in this hub, as the time goes on, sensitivity is dropping. These 3 different beams. But for timing, you can just say that sensitivity is dropping, but at this point you say sensitivity is maintained. And now if you separate out the 3 colors, let's say this is the beam which actually formed from the full GMRT array, all the way up to going to 25 kilometer of baselines. And this is the beam which is formed from the 1 kilometer of baseline. So basically you say, as the baseline increases, that means the antenna number increases, you definitely should see a sensitivity improvement, which you see here. But here you can see the blue line actually falling lower than the red line much faster, because as the baseline length increases, your antenna get dephased faster, unless until you do something called infill phasing, where actually you try to phase the antenna using the fluxes present in the target field itself. So that you have tried and you have demonstrated is working. Now it's getting integrated in the spotlight. When that happens, you'll be able to push the number of antenna higher, and definitely you see improvement in sensitivity. And people have been shown this is very useful for when you do the time domain survey. Just your raw sensitivity increasing. So anything which is based on the raw sensitivity, either it's DM, dispersion, measure precision, or the time of arrival in the millisecond pulses, you see everything is improved because your raw sensitivity is getting increased. So another thing, Candice, which Ujjwal is working on, so is basically to kind of zooming on the DM time plane. So your classifications get better, and it clearly shows that proper zooming with considering the observing frequency DM width of the pulse is actually makes your DM time plane much clearer, and it clearly in your eye you can say, okay, this is the pulse, this is the FRB, this is not. But an AI also does the same way. When you put this kind of plot into AI, you can see that the blue bar is increases, red is a false classification, or the blue is a real classification. So it improves drastically. So that makes the things easier for us to operate at the low frequency. So, and then as any other survey, you have to have AI classifier, and we have there, we are trying to improve the AI classifier. We just start with the phage, which you have heard last week, and some of you have used it also. And we want to build on that. We are also, there is an incoherent dispersion meant real-time imaging pipeline, which you also heard last week. So these are all kind of working and giving us a thing and getting tested and operating. So in this slide, I'm just trying to capture where we are right now. So we have a commensal and as well as open sky mode from last cycle, and 100 hours of time at 160 beam is given to all of you. So anybody can propose and start use that. And then we have this 160 beam mode as more stable from the mid-July. So we had last 1 or 2 months of kind of debugging, clearing bugs and improving sensitivity. And then as you heard from in the morning, that the main motivation is as soon as you develop, put it in the public domain so that people can start using it and actually help us also. So our whole pipeline is there in the GitHub. Then 160 beams real-time pipeline is working from September this last month. And we are already there of 320 beams. So when you come up in a week from now, we'll be on the sky with 320 beams real-time pipeline. And then by end of this year, we should be up to the 640 beams, because that is where we see we can push our system. But beyond that, we have to do a serious development. So that is going to happen for the next year. So hopefully it will be, that's the way we'll be moving on. So that's what you captured here. Few glimpses from the real-time. Things are actually moving like it is, everything is based on web server based. You can actually see the real-time system working. You can see the antenna band shape, phases, and as well as detection. So there is online monitoring tools which can keep on throwing out the detection output. And also we have a discovery page where you actually every observations get logged, so anybody can go through it and check what detections it put through. Similarly, everything is there. So including imaging also, all the plots is getting uploaded there. So one slide for pulsars. So basically, as I was saying, that it also has a periodicity search capability, and it does two ways. One is actually it search for periodicity in FFT, as we heard from the Scott. In the Fourier transform plane, you do this. And second thing, when you look for the fastest pulsar, because as the time resolution is 1.3 millisecond, you can actually, you're sensitive to find a double neutron system, which is tens of millisecond periodicity to the pulsar, slow pulsar up to the graveyard. And so apart from this first Fourier transform, you also have a FFA pipeline, which is the first folding algorithm based pipeline when you are pushing the periodicity search up to hundreds of seconds. We also have 4 coherent dispersed beam is getting deployed, which will be helpful for timing MSPs. Not at the so this beam will not be limited by 1.3 milliseconds. This can go to the much faster time resolution. So it will allow, if there is a MSP sitting in your field of view, you will be able to time. All these in-beam pulsars, RRs, magnetars will be coming out from the 200 beams, which will be getting recorded. So all this part is quite, you heard about a different component of that. So these are all getting developed. Some of them are actually already deployed and is running as a quasi-real-time pulsar search pipeline. And the last part is the LPTs, as you have already hearing, and there is a LPT session also. This is actually one of the most interesting emerging part of the time domain compact objects. So that's what, as this curve also shows, as LPTs are really sitting in the plane, which in the PP dot diagram, where you think that any coherent emitter should not be there, because that's cannot be explained by the normal neutron star emission model. So that's we call a death line, beyond a death line. But the LPTs are sitting there. So this is already posing questions about how the pulsar emission model, whether you need to kind of make some modification, how can you explain them, and what these objects are. So the image domain transient search with GMRT is one of the way to find it, because GMRT is very sensitive instrument, and you have a large amount of archival data present in the GMRT. So that is what this light project is kind of doing, which is kind of a subset of Spotlight, because the pipeline is getting developed there. And we'll be hearing this more from Abhinav later in the week about the pipeline. So this is like one of the 76 pulsar beautifully detected in the image data. And you can see the time domain pulses from there. So this goes through various pipeline, the image domain detections, and then time domain search on each of the pixels, and also the periodic search, because we wanted to find out the periodic, like this is the object is a periodic. So in addition to the single pulse searches, we actually stack them and search for the periodicity. So we basically try to find out, like you can see, periodicity up to hour or so, we will be able to figure out from that. So that's the kind of thing is also getting built up. So now I'll just give this slide here, and then maybe I'll stop. Yeah, thanks.
Thanks, Jayanta. Questions? Any questions from the online participants? Yeah, if online participants have a question, so Ramesh, can I come back to you? There's a question here in the audience. I'll come back to you shortly.
Sure. Yeah, I will wait.
Hi, Jayanta. So where is the advantage of Spotlight and GMRT as compared to other surveys in terms of number of FRBs? Because number of FRBs that you are projecting is 2 per week, whereas DSA, it would be like 10 per day, right? And the other bigger surveys are going to bring more FRBs.
Yeah, and sure. I think the number of FRB, as you see, it's actually much smaller than any large field of view survey can put it. That's basically that is limited by the field of view GMRT has. So the way we see the Spotlight is different. There's one thing is actually the frequency coverage, because if you see, we are going all the way up to 300 megahertz. So we'll be able to see very low frequency things, and maybe you'll be able to see much nearby fainter FRBs. And also, if you see the FRB, like the DMZ plane, there are region where you think we'll be able to probe deeper. That's a region where actually required to have much more FRB. So that is the one way to look at it. And yeah, so I'll just say maybe it has a little bit of complementary space than DSA 2000. I think the way it looks like it will solve many of the problems. So I think, but if you look at the way current population is standing, maybe it has a little bit of complementary area where the frequency space you have not really moved, or maybe the Z space also there are some voids, so we need to fill it up. So I feel the Spotlight will be kind of sitting there, and who knows, maybe it will show us some new different kind of sources.
Yeah, Ramesh, go ahead with your question, please. Ramesh, go ahead.
Yeah, thanks, Jayanta. my question is regarding the BPD net that you mentioned. So I'm just trying to understand, maybe you can elaborate a little bit on what is the idea there. Is it like you do the traditional searching and then you use the classifier to look for the features, or is it like something, a different approach to how you would say, for example, will do acceleration or jerk search, say offline?
Yeah, Ramesh. Yeah, so that is actually based on AI inference. So there you don't do any search. Like normally when you do pulsar search, you do the Fourier transform and then look for acceleration based by the convolution filters. So now if you see that BPD plot, I think there is already a feature which is shown here, which is basically the P and P dot. Where is it? It's gone. Sorry. So PP dot plane. So if you see the PP dot plane, the P is pulsar period and P dot is pulsar or frequency derivative. You can see that there is a bow tie structure is coming out, and that's we know that basically in the acceleration plane the pulsar signals looks like that. So now the thing is that if you train based on this, then you'll be able to see without doing effective searches. So, okay, definitely you are doing the dispersion on the signal. You cannot avoid the dispersion, but instead of doing any convolutions on the Fourier plane, we'll be able to look for this kind of pattern in the PP dot. That's the kind of main motivation behind doing AI inference with pulsar search.
Okay, all right. Yeah, thanks. So basically, this is the kind of plot, say, for example, something like Presto will or similar routines will provide, and you are going to apply AI inference to pull out the candidates from here.
Yeah, this plot you will actually have in, if you actually go and kind of hack Presto, you'll be able to plot this kind of plot because it has this filter plane available in the Presto. But things that this is before convolution. That's something Presto does take power spectra and it's actually convolute various filters and push out that candidate which goes beyond the threshold. But it's not looking at the PP dot plane in one together as a two-dimensional plane. So in one go and looking for patterns. So that's the difference. It's not much, but I think the way we're looking at the problem, that is, if the convolution filter is limiting you, that kind of thing may not be there or may be reduced here.
Thanks.
Questions from the audience?
Yeah, I'm just following up on this. It looks very interesting, but then at the same time, you will be doing a lot of computation to basically compute this plane in the full allowed parameter space.
So these planes are actually getting formed inside. When you actually look for the filters, the way you power spectra things, these are getting formed. But what do you do? Actually, you scan through the plane as different power spectra, okay, and look for the signals and this thing. Whereas now you look at a complete 2D views, and as an image, you look for patterns. And I completely agree with you that this has a computational over it, but this is a nice structure which is present there. And hopefully this will, because otherwise you will be limited by the number of filters you put around y-axis, which will actually how many acceleration you will be able to do. If you go in the kind of if you go as on the frequency derivative plane, whereas in this case you will be actually looking for the various angles.
It's roughly correspond to Z is equal to 200 parameter, and Z parameter 200 or
this one. This actually based on one.
F dot must be coming from there, right?
No,
you do
so Z equal to 200 is the limit at which you can search for in the convolution plane, that how much broader the pulse will be looking for, how much drift. But here I think that this will be limited by the how you can actually differentiate between the angle.
Yeah, I understand, but to what extent you compute this in the frequency derivative, that must also be decided by something, right?
Okay, yeah. So it's here you basically can say it is going up to 200 bins. As you can see, the frequency derivative is going up to 200 bins. So in that sense, it is going up to Z equal to 200 bins drift. It is actually current plot is showing that 200 bins drift. Yeah.
Okay, thanks.
I had a question on the flexibility of your setup, because especially at the highest band, you said there's 2000 DM units. So do you have the flexibility to sacrifice time resolution or bandwidth to go to a higher DM, maybe for just part of the time
Okay. Currently the way these modes are developed, actually, we don't have a flexibility to change these two numbers. Okay. We can change the numbers as the multiplication of these two. For example, if you go to 2K channel, we may be able to push it to 655 microseconds, because this part is actually this beamforming part are actually limited by this part of the cluster. So this is what decides how much beam, how time resolution, and how many frequential. And DM is decided by these two. These two are two different clusters. They are actually connected by 100 gig interface. So the limitation of time resolution and frequency resolution come from here, and then the limitation of number of DM range comes from here. So these two are not connected. So in case, even if you reduce the DM limit, you will not be able to push this resolution up, because beamformer is already frozen at that point.
Okay, I guess we also have to lunch, so we'll thank Jayanta and all the speakers of the morning session.